じゃあここからは、BSB アソシエーションの、ダレン・ケレンシュワ・スティーラーさんからの、お話をしていただきたいと思います。ダレンさんはSPB ワレットの、技術顧問で、今日我々がワークショップでやる、SPB を開発している技術の一番上の人です。で彼がこの SPB について、なんでこの SPB が必要なのか、これを使うことによってどうやってそのビットコインネットワーク全体が、スケールしていくことができるかっていうお話をしてくれますので、ちょっと英語なんですけれども、分からなくてもいいと思うので、ちゃんととりあえず聞いてみて、で終わった後に質問とかを受け付けますので、それは日本語でも英語でもいいんで、日本語の場合は僕翻訳しますので、心配しないで疑問があったら、積極的に、質問してください。よろしくお願いします。
Yeah, thank you so much for the introduction. I appreciate it. So I'm sure you just said that SPV is all about how we can scale the BSV blockchain. So starting just with the general idea, we want to be able to receive a transaction and validate that transaction independently using only data we have. Currently, most of the world is doing things a little bit backwards from my perspective. What we're doing in BSV is we have very large blocks, very large, 4 gigabyte blocks. And with Terranode, we're doing 240 gigabyte blocks or even larger. That's what we're aiming for. At the moment, SV Node is listening to all transactions. And for a lot of wallet operators, they use this listening and indexing to find transactions that are associated with particular addresses from this 11 terabyte blob that is all block data. And then those wallets are retrieving transactions from them, being notified by the node itself. So yes, they can validate this transaction, but it is serious overkill with respect to how much that costs to operate. And of course, if the service goes down, the wallet is without the data it needs, and at very high transaction throughput, this is possible. So if we go back to basics and just think about what is the minimal data we need to be able to validate a transaction, we should define what we mean by validate. So the verification steps made on receipt of a transaction from a counterparty are as follows. We have to do script evaluation. On each unlocking script, the result should be true. In other words, if there's a signature, check sig passes. The sum of the satoshis in must be greater than the sum of the satoshis out. This applies mostly in BSV because, of course, the transaction fees are 1 satoshi, so very, very low. So as long as there is a fairly small transaction, 1 satoshi is enough to cover it. So this rule holds. Each input must be associated with a Merkle path to a block of some sort. So this is what we'll be diving into the details of more today. The fourth point there is end lock time and end sequence. I'm not going to be talking about that today, as it's less frequently used, so not something we need to flesh out today. So considering this wallet that's operating in SPV mode, it receives a transaction. It receives a Merkle path, but it also has block header data. Let's dive into what exactly I mean by that. A block header service could be running connected to the P2P network. So that's the nodes that are mining transactions, and potentially Sybil nodes and all sorts of traffic. P2P network, as we know, the Bitcoin network. It retrieves all headers, so get headers data, and it listens to block announcements. But it also is able to catch up so that it has all block headers from Genesis all the way up to the most recent block that node has heard of. And it can connect to multiple peers to ensure that it's always keeping up to date with the tip. It also provides an API to the SPV wallets so that those wallets can check a Merkle route at any height. So big block data, small header. What's in that header? Really, the two bits of information we're interested in are the previous block hash and the Merkle root. The reason we care about the previous block hash is, well, twofold. The hash of any of these headers is what we would normally refer to as the proof of work. You see the long list of zeros at the end there indicate that we have hashed this data many, many times with different nonces at the end there and even different version numbers, something referred to as ASIC boost. So we all know ASIC machines in factories all over the world are running SHA-256D over this data many, many times so that they can arrive at a proof of work. So we immediately know when we have the block headers that not only does it have a proof of work, but it's also chained to the previous block. So when we say a blockchain, really we mean a chain of hashes, a hash chain, which is just the hash chain held within the headers of each block. If we have the headers, we have a blockchain. The other detail, I want to jump back to this slide in pink here, is the Merkle root. So the Merkle root is referring to the top dot in this diagram, which is a Merkle tree. It's a binary tree, which allows us to contain all of the information that is within the transactions within one block. So for example, if we're interested in this particular blue transaction, the TX ID there at the bottom, all these leaves are different transactions in that same block. And we use the yellow hashes. We combine those branches within this Merkle tree by concatenating them and double shying them to arrive at the hash above. And then we combine that hash above with its levels branch. I can actually use my mouse, I realize here. So we start with the TXID here. We concatenate these, hash to get this green one here. We hash these together to get this green one here. We hash these together to get this hash. And we hash these two together here to get the Merkle root. So you can imagine that if we strip out all the extraneous data, the Merkle path, as we refer to the yellow dots here, is just 4 hashes. And the larger the block gets, the more hashes we need, but it's log 2 of the number of transactions. So if you can imagine a block with 600 million transactions, as Terranode is currently doing, that is only about 1.5 kilobytes worth of data for the Merkle path. So 240 gigabyte block, 1.5 kilobyte Merkle path still. So not a lot of data. And now if we bring that blockchain back in to the top of the screen there, we've highlighted the pink bit there as the Merkle root, which is in a particular block. So now we can validate, does that Merkle root match the Merkle root within a chain of blocks? So we have a Merkle path that comes with a block height. We look up that block height, and that gives us the validation we need that this TXID does indeed appear in the blockchain. That's the fundamental. How much data are we talking? All of the block headers to date, that's 15 years worth, 36 megabytes. It's 80 bytes per block every 10 minutes. It's practically nothing. Certainly below Moore's law by an absolute mile. And of course, the Merkle path is pretty small, as we discussed, even for a very large block. And the transaction data itself is minuscule. So now we can validate that transaction with very, very minimal data. The only problem we have is that we need to wait, because before this transaction is mined into a block, we don't have that Merkle path. So the way we get around this for small casual payments, which we expect to be instant, is we actually get the source transactions for the transaction that we're trying to make. So imagine a wallet is trying to make just a tip, so a very small transaction of some sort. What we do is we look at the pool of UTXOs in our originator wallet, or the person who is paying their wallet. We look up the UTXOs there that have Merkle paths associated with them already, i.e. the transactions that they were created in have been mined. And then we include that data as well as the new transaction which spends one of the outputs. So we'll take a closer look and consider the possibility that we might want to make several tips very quickly in quick succession. And so we might have a chain, I'm going to jump forward here. We might have a chain of transactions which have not yet been confirmed, but we can still go through the process of making sure that we have a Merkle path that is valid and therefore a grandparent transaction, which we know is in the blockchain. And then we can validate that the transaction that's spending that UTXO is also valid in its construction and by the 4 methods that I mentioned previously, and so on and so forth. So this chain can extend as long as is necessary. So jumping back a little bit again here, we're going to take a look at the actual bits and bytes here, because I figured university audience, it's probably okay to go into the depth of the technical bowels of the thing. But this is a transaction format which is specifically designed to allow an SPV wallet to do an evaluation of the background of the inputs of that transaction. So we call it background evaluation extended format. And this maybe makes more sense in English because the acronym is BEEF, which is an easy thing to remember. We also encoded the word BEEF into the version bytes so that it's easy to eyeball as a developer. We have this version bytes at the start. We have bump data, and bump again is just an acronym for BSV Unified Merkle Path Format. So this is the Merkle paths for all of the transactions, apart from the last one, for example. So all of the Merkle paths that we have, we include in this data structure. But more details can be looked up online here. So brc.dev/62 is where you'll find the technical details here in much more depth. But I'm limited in the time of this presentation, so we'll skip over that. The important thing is there's a version number. We have the number of Merkle paths. We include the Merkle path data in a specific format. And then we say the number of transactions. And just like this, if there are multiple transactions, that would obviously just be a higher number. We include this list of transactions, which could be parents, grandparents, etc. And then after each transaction, we have a 1 or 0, just a single byte to indicate whether it has been mined into a block. So 1 if it has, 0 if it has not. If it has, then we follow that with an index number pointing to the particular Merkle path associated with it. So that's the real raw details of this format. Taking a look at an example now, we have the version bytes. We have a varint, the number of Merkle paths. This is a Merkle path format. We have the number of transactions. We have this first one that I've highlighted in pink. And then we have an indicator that this does have a Merkle path and that it's index 0. So this is the Merkle path associated with the pink transaction. And then this final transaction here is, we could consider that the payment we're trying to make. And so it has one input here. I've highlighted the TX ID, which points to this transaction here. So we can hash these bytes, double SHA, and we'll find that that results in this hash here. And so we can connect these transactions in a normal DAG as we normally would. So you can imagine as this gets a longer and longer list, it makes sense to consider, do topological ordering, CAN's ordering algorithm would work, such that we have a DAG basically, so that the final transaction is the one we're trying to make and everything prior can be validated ahead as we're streaming this transaction in and we process it in time. So we process the Merkle paths first, and then we start with the oldest transaction and so on and so forth until we arrive at the newest transaction, which normally does not have a Merkle path associated with it. So again, just referring back to this chain of digital signatures, which is how we define Bitcoin really. So if we have the Merkle path, we can validate the transaction and so on. I bet you're thinking now, well, with the blue transactions, since they're not confirmed in a block, how do we know that, say, the person sending this transaction hasn't already spent the inputs that are being spent in these later transactions? Since they haven't been broadcast yet, it's possible. So I just want to point out that the thinking here is that these transactions are peer-to-peer. They're between two human beings usually, And certainly if they're between machines, then they're very low value, casual payments that we're not too concerned about people going to loads of effort just to manipulate a particular service. If it's a few cents, the work needed to do that would be significant enough that it is not economically viable for someone to exploit. If we're talking significant payments of any sort, then we're talking about transacting with real human beings. We know who they are prior to any payment being transferred. And this is a legal requirement. So for small casual transactions, it's not a requirement. And so we can sort of dismiss that as probably overkill in terms of verification. And obviously confidence with this chain, confidence grows as we get more and more green transactions with Merkle paths. So we can make a value judgment there as to how much validation and verification we need. But for most cases, we know who our counterparty is. And so between us, given that we are transacting, we do know whether those UTXOs are spent or not. Because if Alice is sending Bob this transaction and she's saying to Bob, I haven't spent these inputs anywhere else, and she's signing across some data that she's handing over a chain of digital signatures that allude to that. And so if something were to go awry, if for some reason Bob had to leave the country within 10 minutes, as unlikely as that sounds, if that were to happen, then there would be recourse, basically, because Bob has a bunch of signed evidence that Alice is coming forward with a chain of digital signatures. So if she is defrauding him, then she's also handing him evidence of her fraud, which doesn't make any sense. So again, like most things in Bitcoin, the security model is economic in nature. So as long as Alice knows, Bob knows. Let's take a look at the broader picture of how SPV works within the network topology. Alice's SPV wallet creates the transaction that she signs, sends directly to Bob's wallet. So not through the peer-to-peer network, but literally through a connection, either say Bluetooth, even near field communication. It could just be a simple web API. The point is Alice is handing it directly to Bob. She keeps a copy, Bob keeps a copy. Bob then passes that transaction onto a service layer or an overlay network, which also retains the transaction before propagating that to the mining nodes. We refer to the mining nodes as Terranode, which is the new software Jake will be discussing just after my presentation. So again, Terranode is assembling blocks. It's competing with other miners to find a proof of work. And when it does so, or when anyone does so, part of its systems will calculate a Merkle path and send that back to the originating overlay service. So now we have a validated transaction in Terranode. We have a validated transaction in the overlay. And that overlay will reach out to Bob, who sent it the transaction. We have a confirmed transaction in Bob's wallet, and so on and so forth. So now, all parties to that transaction, everyone who needs a copy has a copy and knows for sure that it's valid and unchanged. So why isn't this used already? Why is this so uncommon? First 15 years, very few people have used SPV in this form. So if we cast our minds back to 2009, I heard from Ken there was some conversation about the various forks and so on. So this again is looking backwards and seeing that we have very much just the peer-to-peer network. Everyone's running roughly the same software, and there's not much topology to this network. It's very much just a kind of rat's nest, and perhaps the three in the middle there are serious miners, but everyone else is just CPU mining. So these are each Bitcoin nodes. Fast forward 9 years, and in 2018, we had some topology that looked a little bit more like this in the BSV space. We had Mappy, which was a way for serious miners to expose a web API for broadcasting transactions to a very well-known miner. So there were a couple of those across the world. And most web applications weren't running Bitcoin nodes. They were running just standard web applications with wallet code but they would send the transactions to these MAPI services to get them mined into blocks. The MAPI service would give them callbacks once they were mined. And they would sign across them saying, we have verified this. So you're externalizing the verification process in this era. So if we jump forward to, oh yes, and some people were running on premises as well. If we jump forward to 2024, we have a scenario where there is a very different network topology forming. So at the center there are teranodes, extremely serious, high throughput, state-of-the-art, building massive blocks, 240 gigabyte blocks. That's 1 million transactions a second. So surrounding that inner core, we have application-specific overlays. And around the edges there, we have user devices running SPV. So perhaps we have a yen stablecoin overlay network on the left here. Perhaps there's a couple of service layer overlays running SPV for yen stablecoin. So they would be propagating transactions, as I described earlier, to the center of the network, and they'd be propagating the Merkle paths back to the green user devices. And it's important to note that there are many different services that can all have their own specific interest in a particular area of all transactions. They can focus on specializing their service to handle those particular transactions. And users of SPV services are free to roam around this network using different overlays at different times. They're not stuck on one necessarily. And you can see I've intentionally made connections between them because it's a peer-to-peer electronic cash system. So they're passing these things between each other, and they're using overlays to broadcast these transactions. So, arigato. And are there any questions? Happy to take them in the final 2 minutes before I pass on to my colleague, Jake.
Awesome. Okay. I'm okay to start. Awesome. All right. Well, thanks for having me. I think Ken introduced me. That's what you were just doing right now, right, Ken? Okay, perfect. So I'm going to talk today about Teranode overlays and what we're calling the blockchain mandala. If you're familiar with a mandala network, it's a network that consists of a bunch of the same shapes. So if you think about it, it's a bunch of the same patterns or shapes concentrically, usually in a circle around each other. And that's kind of like what the Bitcoin network is becoming, what it's meant to be. We'll go through that today. Sorry, Ken, did you want me to like pause so you could translate or just continue through? Okay. Perfect. Sounds good. So I'll take you through 3 parts today. The first is going to look at what the competitive advantage of BSV is, but really what the competitive advantage of blockchain is. And then I'll take you through Teranode, which is the new node software that we're currently building. It's being tested right now. We're looking to have it on mainnet by the end of this year, so starting next year. And then we'll finish off with ARC, which is a new transaction processor that we have, and overlays, which ARC kind of leads into. And that'll cover kind of all of the pieces of the network, starting from the concepts and the idea behind the network, behind blockchain, going from the nucleus of the network outward to the edge. So starting out with BSV's competitive advantage. And I do say blockchain's competitive advantage because really anything that you can do with a blockchain, you can do with servers as well. What ends up being a competitive advantage of blockchain, the major problem that it solves, is micropayments. And so this is actually in the Bitcoin white paper as well. The system was designed to enable small, casual payments. And it's the first time a system has been able to accommodate that. If you think about how much it costs for Visa or MasterCard transactions, it's prohibitively expensive if you're trying to use them for sub-cent or sub-dollar payments. And so what blockchain does is it uses a competitive system to add unbounded scaling, specialization, and P2P communication to the network to allow micropayments to take place, particularly at the edge of the network, using P2P or person-to-person communication. So this is what the current BSV network looks like, and the most current blockchain networks. You have a network of nodes, and then you have users that talk to the nodes. So the problem with that is it's only 2 layers, and if you want to have unbounded scaling, then you need specialization, and if you want to have P2P communication, you need those 2 things as well. So to accomplish that, we need to add more layers to the network to allow that Mandela effect to start taking shape. So we want to enable people to make their own decisions and almost form kind of their own mini networks. You should be able to talk directly to the person that you want to transact with, and they should be able to talk to you, and you shouldn't have to talk to any other entity to make that communication possible. So right now, what happens is you have to talk to one of the center nodes, and then they have to do something with your information. They have to basically steward your information and send it to the person that you want to talk to. And so that makes them a trusted third party to your communication. And so what Bitcoin does, what BSV does, is it solves that by allowing you to communicate directly with another person. And then that receiving person can timestamp the transaction onto the main chain. And that's Section 8 of the Bitcoin white paper. It uses a process called simplified payment verification. And so the problem we currently have and what Terranode is solving is it's breaking through the barriers and limitations of our current node software. So because our current nodes are responsible for not only timestamping transactions into blocks and competing to add blocks to the chain, but also all of the other aspects of the blockchain, like serving data and returning Merkle paths or Merkle proofs for SPV, etc. It limits the capacity of them. So in order to break free of that, we need to make sure that they're only doing one thing. And so even today, further to that, in order to use the blockchain, if you're not looking to mine, you still have to run a full node, because you want to get the information on the blockchain. You have to have a node that's talking to all of the other nodes on the blockchain. And that's obviously really expensive, especially if you want to accommodate micropayments where you're getting more and more transactions and more data being put onto the chain. So this is what we're working towards. This is going to be the future of BSV and ultimately the future of blockchain. And so if you look here, we've essentially added a third layer, and this is a naive diagram. So really this third layer is many layers. But if you think about it in this way, the center is the nodes, or the small world node network, and that's followed by a service layer of overlays. And those overlays don't necessarily have to live in that layer. They can really be anywhere in this network except the center. And the outer layer is the application layer. And so the way this works is you have the outer layer talking directly to each other and directly to the overlays. And then it's the overlays talking to the node network. And the node network is sending responses out. This will ideally be done using IPv6 multicast, so everybody can just subscribe to a standard set of group addresses and get the information they want. And then it's the overlays that are giving the responses back to the users, or the users giving responses back to themselves, each other, I mean. And so that improves scalability because you don't have so much load being put onto the mining nodes at the center of the network, and it also improves privacy and just overall usability of the chain, because you're breaking things down and you're specializing them. You're allowing them to take place at the edge of the network rather than forcing everything to go through the center of the network. So now I want to move into more of what Terranode actually is, what we're doing with it. So just to give you an idea of the architecture, what Terranode does is it takes a proactive approach, and I'll talk more about subtrees in the next section, but ultimately what we've done is we've taken all of the different aspects of a mining node, Bitcoin mining node, which is described in section 5 of the Bitcoin white paper, and we split those out into separate services. So instead of having one monolithic machine that's taking care of everything, we have a set of microservices and services that divide the work up, and that makes the system horizontally scalable. And ultimately, the goal is to make it unboundedly scalable. But there's a slight hiccup with the block assembly piece, but we're working on that. So just to give you an idea, these are the different services and microservices that make up the Terranode system. We have the propagation service, the transaction validator service. I don't know if you can see my mouse. Transaction validator service, block assembly, blockchain service. I can just kind of briefly take you through what each of these do. So the propagation service receives new transactions, and then it sends them to the validator service. And the validator service checks the transactions for correctness and adherence to the network rules. And then it sends blessed transactions, we call them. So once the transaction validator service has validated a transaction, it stores the relevant data, it updates the store, it stores relevant data about the transaction in the transaction metastore. And actually, it's the propagation service that stores the transaction itself, although that is a feature that you can turn on or off because nodes do not need to keep the full history of transactions. That's the responsibility of overlays and users, but they do need to keep information about the transactions in order to build blocks. So once the transaction validator has stored that information, we consider that transaction blessed, and only the transaction ID needs to be passed to the block assembly service. And so the block assembly service is responsible for assembling blocks, and to do that, it actually assembles subtrees. And I'll explain how that works, because the blocks use Merkle trees in order to organize transactions. And so those Merkle trees could be split up. And then, as I was saying, it takes a proactive approach, because instead of waiting every 10 minutes to send a block around once a block is found, it actually sends those subtrees out to the rest of the nodes of the network as soon as they're constructed. And so by the time a block is found, all the nodes on the network have more or less all of the transaction data, and it's all been validated already. So it's very easy for them to quickly validate that found block and continue mining the next block on the chain. Next is the blockchain service, which manages block headers. Then there's the block validation service that validates subtrees and blocks. The transaction store is pretty obvious. I just talked about that. It's not an integral piece, but it is important if you want to hang on to transaction data. Likely what you would do though is you would split that out as a separate service, and you would store transactions in probably an archive format. And if people wanted to access those old transactions, they would have to pay a fee to do that. Just to give you a little bit better view there. So this is the transaction ingress egress. It's coming into the propagation service here. going to the transactions being stored, and then it's going to the transaction validator. If it's rejected, if it's invalid, it goes back to the propagation service and gets propagated out to a multicast group, or however it's being communicated, the P2P network, peer-to-peer network with all of the other nodes. If it is valid, then the relevant information gets stored in the transaction metastore, and the blessed transaction ID goes to the block assembly. Ken, just to make sure that I'm not losing everybody here, is this level of detail okay? Everybody following along? Okay, for sure. Yeah, no, and there's quite a few pieces. Okay, so what I'll do is I won't go into detail too much about that, but I will cover the subtrees, because that's an important piece. So the subtrees work by splitting up the Merkle tree within a transaction. So you have the transaction is made up of a block header and then the Merkle tree of transaction IDs that are within that block. And so all you need for the block header is the very top hash, because how a Merkle tree works is you have your bottom items here, the hash of your bottom items, and then you create the rest of the tree by hashing those bottom items together until you have one hash left at the top, and that is the Merkle root of the tree. But what you can do then is you can carve out subtrees from that Merkle tree, or you can construct subtrees as we're doing in Terranode, and you can send those subtrees around, and then all you need to build the rest of the tree, or to get your Merkle hash, your root hash, in order to create what's called a block candidate and send that to the miners for mining. You just need those hashes from the top hashes from the subtrees. And so that's kind of the magic that's happening in Terranode, other than the distributed nature and all of this, the microservices, is we're using this proactive approach and sending these subtrees around. And just to give you an idea, at 1 million transactions a second, these subtrees are being sent out every second. So lots of communication happening, and it'll become even smoother once we get IPv6 integrated. We're still working on that. Any questions so far?
This subtree is the shared with among the miner, or just inside the miner, one miner?
Yep, it's shared amongst all of the miners. So as soon as a subtree is constructed, right now Terranode constructs subtrees of a maximum 1 million transaction IDs. So once a subtree is fully constructed, it's immediately shared with all of the other nodes on the network. So the nodes have the information necessary to validate a block once one is found.
So they don't propagate the single transaction anymore. It's just more like they just bundle it and make a subtree and then share the transactions that way, or
they do still propagate transactions, but the ideal scenario, what we're aiming towards, is transactions coming into the network are going to be propagated by a multicast. So it's safe to assume that nodes basically have the same transaction data. They should be getting that transaction at roughly the same time. So then it becomes a matter of getting that information around the network as quickly as possible. And when we're talking about the scale of 1 million transactions per second, it becomes a challenge to send full blocks around, full block information. And if we're doing subtrees, then we don't actually need to do that. We can just send the block header information. For sure. So this is just the format. So this is a subtree, and as I was explaining before, we have the transaction IDs, and then we have the Merkle root, and we have the height of the tree. And then to construct the block, we have the block header, Coinbase transaction, and all we need are the subtree IDs. So it's a nice, easy way and proactive way to construct blocks. This is just going into a bit more detail about that. I don't need to go through that. I'll just skip ahead here. That's validation. I can take you through extended format. So extended format is another innovation that actually was first introduced with ARC. But what it does is it adds a couple of fields, or a few fields, I should say, to transactions so that extra lookups don't need to be made. So raw transactions don't have the input data needed in order to be fully validated. And so what extended format transactions do is first they mark whether or not the transaction is extended format. And they do that just by having a few extra bytes there. And then they add the necessary data needed in order to validate the transaction to the end of the transaction, the raw hex transaction, or the raw bytes, I should say. And so with this information included in the transaction, those extra lookups on the input data don't need to be made, and it makes things quite a bit faster when you don't have to do extra lookups. Any questions on that?
Yeah, it's my question. So the extended format is you basically got the input value inside the raw transaction, right?
Input. Sorry, I missed the second word there, Ken. Yes, it's so the inputs to fund the transaction. Like a regular input is you just have these pieces, right? Like you have your previous transaction hash, and then you have the output index, script length, the scripts, and the script itself, and then the sequence number. And so when that transaction is submitted, the information needed in order to validate it, so the output script, in order to validate that the input script against it, needs to be looked up. And so what extended format does is it actually includes that output information in the same transaction. So the lookup in order to find these three last pieces doesn't need to be made.
So the wires are going to produce the extended format to broadcast it, or how?
They could.
Are they going to change the transaction format completely, or?
No, and this doesn't change the transaction format completely. It just adds extra information to it. So it's not actually changing anything about the transaction. It's just bundling more information within it.
So it's kind of edit the extra information on top of the raw transaction.
Yeah, you just append it to the raw transaction.
Input the Satoshi value.
And Darren also put forth a couple of other proposals. Bump, which is one that can be used to include Merkle paths, and Beef, which is an augmentation of the extended format to do the same. I think he can correct me if I'm wrong, but it essentially adds Merkle path information and the extended format. So it's just a way to improve the efficiency of sending the information through. So extra lookups don't need to be made, because at scale, as we've been learning, those extra lookups make a really big difference to performance. And if we want micropayments, then we need to start thinking about that from now. We want to enable as many micropayments as possible. It needs to be unbounded. Is it any more questions? Does that make sense? Sounds good. So the last section I'll just take you through quickly is ARC and overlays. So ARC is the transaction processor for Bitcoin. And so it was made as a replacement for MAPI in order to submit transactions to the network, and uses the extended format. And so you can see the difference there. The left is the standard form, and the right is the extended format form, and the fewer steps needed. So it's kind of shown nicely here. When a transaction is created and the UTXOs are added, signed, the raw transaction is sent. So for each input in that transaction, a previous transaction or missing inputs need to be looked up. Whereas if that information is included in the transaction, it can just be validated as that one package and communicated forward. So this is the architecture of ARC, and we don't need to go into this into much detail here, but I'm mostly including this so that we can see the difference in the end for the overlays. Yeah, we don't need to go through that. So did Darren go through overlays in the previous lecture? I'm sorry. Okay. Yeah, so if I'm repeating anything, just let me know, but I'll just take you through this quickly. So overlays, as we talked about before, it's that middle layer between the users and the nodes. And traditionally, an overlay usually refers to a virtual network that's on top of an existing underlay or physical network. And it provides services like routing or peer-to-peer networking, or usually it enables things like distributed computing, and like GRE tunnels is an example of that. But in Bitcoin, it's a little bit different, because instead of thinking about it from the network perspective, because Bitcoin is inherently distributed, and when we're talking about transactions, we're talking about commodity tokens, and it's actually the tokens themselves that are being communicated. Instead of an example of, or I guess an analogy to this would be in a GRE tunnel, what makes the tunnel a tunnel, more or less, is you're adding or you're wrapping the packet with the extra information necessary in order to make it a GRE packet. And so when it's sent from one side to the other, the receiver is able to then unwrap it and know what's inside of it. And the underlay, or what's communicating it, doesn't really care what's inside, and it allows you to bridge gaps that you couldn't otherwise. But with BSV, with Bitcoin, it's a little bit different, because we're not actually having to create these connections between receivers. What we can do with overlays is, if we think about them from transactions first, we can use transaction types, which we can mint or create. And as long as we mint or create them in the same way that the commodity tokens were created, they were all instantiated at the same time, so we have a set amount, then as long as, and if we think about how SPV works, if you have the chain of block headers, you can run the check against the block headers. It's essentially an integrity check. We can do the same thing with tokens. And so as long as you have the list of hashes or integrity checks for each of those tokens that are created, you can communicate those to the nodes that are part of the overlay network. And anytime they receive one of those tokens or one of those transactions, they can run an SPV check on it to make sure it's a valid transaction, as well as an integrity check to make sure It's the type of token that that overlay understands. And so the other reason why this is kind of important is, in order to get the scaling necessary and in order to get the micropayments working the way we want them to, we also have to get away from thinking about the blockchain as a server where we store data, we store information. Although we can store data on chain, and it's not necessarily bad to store data on chain, it's not possible to accommodate that data and to do reads from it or use the chain as a server, especially when we're talking about scaling it up and using it for micropayments. So we need to shift our thinking from the chain is a server to the chain is like an integrity check system. It's a time stamping system, and it allows us to store information anywhere, and we can be sure that it's the correct information, that it hasn't been tampered with, because we can run an integrity check on it using that main chain that's competitively maintained. And so it replaces the need for a trusted third party. We don't have to trust where we store it, because we can run a check on it and make sure it's the real data and it hasn't been tampered with. Let's get that. So this is Darren actually put these last slides together, but this is a good way to think about overlays or the transactions within them. So if we think about this blue square as a block, and these yellow lines are yellow transactions, the green lines are green transactions, and so yellow transactions are part of one overlay, green transactions are part of another overlay, and then the red transactions are part of both overlays, or both overlays understand them. Then you can see how all of them are part of the block, but they're only understood by certain entities. And so the idea here is just to show you that the Satoshi tokens, the commodity tokens that make up a transaction, they can be understood by any overlay in any context. But what you can do is you can add context on top of those. You can overlay them with context, and that overlaid context can only be understood by the overlays that want to understand it. And so it provides a nice way to keep the form of the distributed nature of the blockchain, while also unlocking all of those extra things that the blockchain can do, and allowing the nodes to just focus on timestamping transactions and adding blocks to the chain. So this is just a further example, but we don't need to go through that stuff. I'll just skip ahead to some of the example use cases. So what we can use overlays for are things like fungible tokens and Satoshi tokens. The commodity tokens actually are fungible tokens, so we're just maintaining the properties of those Satoshi tokens. And then non-fungible tokens, we're adding some extra properties on top of that to make them non-fungible. Open predicates, competition for computation markets, data predicates. We can add rules to certain transactions to make it so that the person storing that data doesn't get paid unless they store the data for a particular amount of time. And then backup services, explorers, and this is where we are today with our ability to make overlays happen. The orange blocks are what we're kind of missing. But what's so exciting about this industry is even this right here, what we're talking about today, that's changing all the time. So there's even parts of this that we can already update. And this is what we're hoping to achieve in the future. This brings the IPv6 multicast into the picture. And so with multicast, what we're aiming for is to be able to have those set group addresses so that transactions can be submitted to the set group addresses and all of the nodes are receiving those transactions. And then even overlays can tap into those transactions or those group addresses, I should say. And so if they want to receive certain transactions of a certain type, they can actually tap into that feed and then add some kind of a filter to filter out all of the transactions that don't fit into the overlay. And just to finish off, if you remember the arc diagram, it had the line going from the node back into arc. To achieve an overlay, all we do is we replace that part with localized storage. And so it's just to kind of drive home that point of not thinking of the blockchain as a server or a data store. You want to store your data within your overlay, which is likely how you're storing it right now. And then you're using integrity checks and the blockchain to just ensure that it's the correct data and that you have the correct history, etc. And so those are all the slides I have today. Let's open it up for questions.
ブロックチェーンはすごい、マイニングをするのにすごいエネルギーを使っていて、AI とかもその電気使うけどその、何万倍、10万倍くらいの電気を使っている。それだけの、電気をかける価値があるんでしょうかっていう質問をしてたんで、それを聞いてみましょう。Hey, Jake, one question is that it's more like a blockchain or proof of work, all of them. The question about mining, the block, in order to mining a block, we are spending a lot of energy. Even AI spends a lot of energy, but we use like hundreds of thousands more times energy than AI currently. And do you think so? How we can justify the energy we are spending for the blockchain?
Yeah, for sure. So blockchain is actually way more efficient than current systems because yes, it uses a lot of energy for proof of work, but by making the blocks unbounded, by having the ability to add as much information as you want into each block, you actually counteract that because you can add so much information per block. The proof of work or the mining part of it doesn't change. So it doesn't matter how much information you add to the block, the work done in order to find a proof of work solution doesn't change. It's decoupled from the actual processing of the block information. So it becomes more efficient over time or as the blockchain gets used more. Appreciate it. Thanks, Ken. Thanks, everyone. Bye. Arigato.